Hello everyone, my name is Romeo and I'm the president of the Biophysics Club for 2020 to 2021. This video is meant for the virtual club fairs, but it will be public, so if you stumble upon it or someone recommends it to you, then there will still be ways you can join the Biophysics Club. And hopefully this video will keep you interested. And so what I'm going to talk about are what is biophysics, what the club does. I'll give you hopefully a cool demonstration in which I will explain how it works, and I'll give a biophysical application of that demonstration. And so, firstly, what is biophysics? So biophysics, it's basically taking biological problems and we solve them using physics. The most common one that people know are imaging the body, like ways through MRIs, PET scans, CAT scans. These are all biophysical applications or biophysical methods to image the body. But there are also many other applications of biophysics. In terms of food sciences, agriculture, pharmaceuticals, computational science, biophysics is everywhere. It's a very broad field. And then I think that's one of the reasons why it's so interesting. It could be used in just so many different places. Surprisingly though, even though it's such a diverse field, not a lot of people tend to know about biophysics. I actually didn't know about biophysics until grade 12 when I was reading York's undergraduate programs, and I saw the word biophysics. I really loved bio and physics, and I wanted to combine them together, but I did not see that anywhere, except in grade 12 when I saw the word biophysics. The purpose of the club, or at least one of their purpose is to make sure students are aware of what biophysics is, and to show that it can be very cool if you're an science enthusiast like me, and just want to see some cool stuff using biophysics. And so the club does this by holding an event. We try to do it like once a month at least. And these events can range from prof talks, where professors talk about their research that's biophysics related. Movie nights, where we'll watch movies and discuss the biophysics behind them. Social events, where we'll all come together and just talk about biophysics. And many other different events. So I'll say this now, if you're interested in joining the club, there will be a push button in the virtual club sphere which will take you to a Google Forms. You just put in your name and your email. We'll put you in our members list, and you'll receive important emails regarding our events or just important information about the club in general. There's also our Facebook page link, which you'll find in our virtual club sphere profile as well. It's basically our club website, if you want to call it. You get the same information as from the emails, but it's in a more, I guess, organized format. So you don't have to look through all your emails. You just have our Facebook page. If you just stumbled upon here or someone recommended our club to you and you're watching this video, you can also join the Biophysics Club. But I will put the Facebook page link in the description, and I'll also put the Biophysics Club email in the description. So you can email us. Just tell us your name and that you're interested in being in the members list. Or even if you have any questions about the club or comments about it, then you can also email us about that. And so that's what biophysics is, and that's a bit about what the club does. So right now I want to do a demonstration that's biophysics related, and maybe you've seen it before, but hopefully you don't know how it works, so I can explain how it works for you. And it's literally just taking a coin and then making it disappear with a glass of water. Okay, so here's our apparatus, including my water bottle. This experiment is very safe. You can try it at home. It won't harm you. So we have our coin over here, a quarter, and we have our glass. And then you can see, if I put the glass on top of the coin, you can see that the coin is still there. You can see it from any angle. You can see it from the top, the side. You get the point. But now, if I pour some water into the cup, you will not be able to see the coin anymore if you look through the side of the glass. It is not there. But if you look from the top, you can see that the coin is there. And this phenomenon is actually called total internal reflection, and that's what I'm going to be explaining now. Okay, so I'm going to try and explain total internal reflection with as little math as possible, but we are going to need it a bit, so bear with me. And also bear with my drawing, it's definitely not the best. But here we have Snell's law. It's a very important formula for optics and total internal reflection as well. So These thetas, they don't really matter at the moment, but these n's, they really do. So n, that is the index of refraction for our material. As we can see over here, it's defined as the ratio between the speed of light in a vacuum, which is c, divided by the speed of light in our material, like water or glass, etc. And basically, this tells us how fast or how slow the light is moving compared to a vacuum. So, the higher up n goes, the slower that light actually is in the material. So a couple of examples over here. We have n of air is 1.00, but that's approximated. We can put a whole bunch more decimals, and then we'll see that the speed of light in air is a tiny, tiny bit slower than the speed of light in vacuum. And we can see the n of water is 1.33, and the n of glass is 1.51. So it's even slower in water and even slower in glass. And this is due to the weird bonds and the interactions happening in both the water and the glass, which interferes with the light and causes it to move slower. So now we need to move on to the conditions of which total internal reflection occurs, and there's two of them. So the first one over here is called theta c. This is called the critical angle, and this is the angle that can be derived from Snell's law, and it's basically the starting angle of where total internal reflection occurs. So if theta c, for example, is something like 48 degrees, and then anything above theta c, like 49, 50, 60, etc., total internal reflection will occur. But anything below the critical angle, like 45 degrees for my example, will not cause total internal reflection. And the second condition that needs to be met is that the index of refraction of the first material has to be larger than the index of refraction of the second material. And with both these conditions met, total internal reflection will occur. So now let's move on to our demonstration. And over here, the drawings, we have the little red over here representing the coin, the black represents the glass, and the green represents the light rays emitting from the coin. And so we can see that no matter where the light goes, it's going to end up going through the glass and then ending up on our eyes, which is why no matter where we go, around the glass, on top of the glass, we can still see the coin. And if we look over here, you might say, well, here, it hits the glass, so N1 is actually 1.51, but N2 is the air, so 1. So N1 is actually greater than N2 in this case, but the critical angle does not occur over here. And like I said, both these conditions need to be met for total internal reflection to occur. So the critical angle isn't met, and the light goes through the glass and into our eyes, and we can see the coin. However, when we fill it with water, we can see now when the light goes, it bounces from the glass and onto the opposite direction. And the reason why this occurs is that we still have N1 is glass when it hits it, and then N2 is the air when it's supposed to go through the glass. So our first condition is met, but when we pour the water in, it turns out that the initial angle that the light shoots off at, no matter what ray we choose, it's actually greater than the critical angle. So now this condition is also met. We have a critical angle, or an angle that's greater than the critical angle, and thus both these conditions are met, and that when the light hits it, it'll just bounce off into a different direction. And then this is why, when we look around the glass from the sides, we cannot see the coin, because all the light is hitting the glass and then bouncing off to somewhere else. It's never exiting the glass. And then over here, the critical angle is not met, but N1 is still greater than N2. So both these conditions need to be met for total internal reflection to occur. And then since the critical angle isn't met here, when we look on top of the glass, we can still see the coin from the bottom. If the critical angle did occur, then the light would just be bouncing all around in the glass and never exiting the water or the glass, which would also be kind of cool, in my opinion. And so now we know why we can only see the coin from the top and not from the sides when there's water in it. In terms of a biophysical application, or just in general why we care about total internal reflection, it's actually the reason why optical fibers are able to work. Optical fibers, their main purpose is to basically transmit a bunch of information, or light. Light can be denoted as information, from one place to another very quickly. And so these are used in a ton of places. In medicine, computation, you can find optical fibers like anywhere, basically. And so, telling you a bit about how optical fibers work. Here, we're just taking a little sections of the tube, or the optical fiber, and then the green, again, represents the light. And so, the way the optical fibers work is that here's N2, as we see the actual tube, and then here's N1, which is inside of the tube, so the little cavity in the tube. And so, when the light hits the actual tube, the optical fiber sets it such that N1 is greater than N2. So in the cavity, N1 is greater than N2, which is in the actual tube intrinsically, in the material. And so when the light hits it, it'll just be like this situation from the glass, and then it'll bounce from the opposite direction. And then this will keep happening, as you can see over here, it's like a triangle wave, until it reaches its destination. And in which we see a complete exact image of what happened from the other side of the tube, because all the information or the light was transmitted through the optical fiber. And a biophysical application of this, there's many more, but just one that I thought was pretty cool are the uses of endoscopes. Endoscopes actually have a bunch of optical fibers in them, and the only reason they work is through total internal reflection. And it's explained by this little part over here as well. So first, we have this diagram. Here's our endoscope, and again, green just represents the light. And the red part indicates some part of your body that the endoscope's looking at. And so if we take a little light source, because the endoscope has a bunch of optical fibers, multiple connecting to a light source, and then multiple others connecting to receive the light source. So the light source will shine light, and then, for example, here, this light will bounce down, and then it'll bounce back up, back into the optical fiber. Or it'll shine a light in a different direction. Here, it'll bounce, end up back up in the optical fiber. So my point is, no matter where the light goes, it'll bounce back into the endoscope. And so there's another bundle of optical fibers, if we move over here, that will take this light in and will transfer it back over here to the actual eyepiece of where the doctor is looking. And so, since total internal reflection occurs, none of the imaging over here is lost. What you see through this optical fiber is exactly what the optical fiber sees, if you want to say it like that. If total internal reflection didn't occur, we might actually have some light lost, and then that will make the image or video a bit more noisier, and it will be harder to see what's actually inside your body. So that's a cool application of total internal reflection. And I hope that you learned something new, or you learned something interesting at least. And if you want to join our club, I said where you can find us. And I really hope to see you all in our future events. Thank you.